All right, hello everyone. So what I'd like to do is talk about a really important and interesting application of conservation of momentum, and that's to try to understand how rocket propulsion works. How does a rocket work? So this is a simple example, and I think all physics students should sort of understand this deeply. And the way you understand something deeply is you understand it from different points of view, as many different points of view as possible. So in terms of momentum conservation, there's two different ways to think about that. So one of them is we have, say, an isolated system, and if the momentum somewhere in the system goes down, then the momentum elsewhere must go up. So the total momentum, the total quantity of motion in that isolated system remains the same. In application to the rocket, we have, say, one part of the system, of the whole, is a rocket with momentum to the right, but it's also spitting out exhaust gas particles, which have momentum to the left. And so if the momentum of the rocket increases to the right, well, that's because it spit out some more exhaust gas particles with momentum to the left. And so the total momentum, the total quantity of motion in the isolated system didn't change. So if a rocket starts off at rest, it has total momentum 0. Then if you account for the momentum of the rocket, the forward momentum of the rocket, plus the backwards momentum of all the exhaust gas particles, the total momentum will never change. It will always be 0. Okay, another way to think about it, conservation momentum, is in terms of momentum transfer. So momentum is transferred when mechanism is a force acting over time. Well, we have a thrust force acting over time on that rocket, and that transfers momentum to the rocket. Okay, so but before we get into all the details of that, what I want to do is make sure that we understand how a rocket works just intuitively, sort of in our gut. Okay, so so what I want you to imagine is a situation where you're in a boat and you're out in the middle of a lake, and the weather's very calm, there's no wind, the water is perfectly still, and you're sitting out there, and you would like to find some way to propel the boat in that direction to go to shore. Okay, so then you think, if I had a paddle, what I would do is I would take the paddle, I would stick it in the water, and I would pull back on the paddle like this. And what you're really doing is you're pushing against something. The paddle is in the water, and the paddle is pushing against the water. Okay, and so, but then there's an action-reaction, third law, Newton's third law, right? So basically, your hand is pushing on that water, through the paddle. The paddle itself is compressing a little bit, the handle of the paddle, like a spring, and it pushes back on your hand. And so while you're doing this with the paddle and pushing that way in the water, making the water accelerate that way, the paddle is pushing back on you and making you and the boat accelerate that way. Okay, so that's the basic idea. So the key thing here is if you want to change your velocity, you need to be able to apply a force. You need the acceleration, you need to be able to apply a force. And forces always come in action-reaction pairs. And if you have nothing to act against, if you have nothing to push against, well then you can't go anywhere, right? So if I've got a wall here, I can push against that wall and I can make myself accelerate this way. But if there's no wall, I can't make myself accelerate. If you're floating out in the middle of empty space, doesn't matter what you do, wiggle your arms here and there or whatever, you can never move your center of mass. Okay, so you need something to push against. Okay, so suppose, oh no, I forgot the paddle. Can't push against the water. Okay, so then, but you notice, wait a minute, there's a pile of cannonballs right here inside my boat. So, what am I going to do? Well, you'll pick up a cannonball which has some mass, like inertia, and you take that cannonball and you throw it this way, and that will propel you and the boat and the rest of the cannonballs that way. And so why is that? Well, same reason. You have something to push against. Okay, so here's this cannonball, this massive object, and while you are pushing, what you're doing is you're exerting a force on the cannonball that way, which causes the cannonball to accelerate that way. But at the same time, that cannonball, while you're pushing, is slightly compressed, and like a little compressed spring, it pushes back on your hand. So the whole time that you are pushing that cannonball that way, that cannonball is pushing back on you this way, causing you and the boat and the other cannonballs to accelerate that way. Okay, so let's actually talk about this in a little bit of detail. Okay, so what we've got here, we're going to say that this box here is of some mass, big M, and this mass represents the mass of the boat and all the cannonballs in it. And what you've done is you've picked up a cannonball. This cannonball has a mass little m, and the idea is you're going to exert a force on that cannonball. But of course, when you exert a force on that cannonball that way, then there has to be a force exerted on the rest of the boat that way. And so now what we're going to do is we're going to replace me, which is sort of a really inefficient, complicated machine. We're going to replace me with a compressed spring that we're going to let uncompress. Okay, so we're going to attach a compressed spring between the cannonball and the boat. And if you think about it, this is a very good, simple physical model, right? Because what's really happening is I am here and I am pushing on the cannonball. So what I'm really doing is I'm sort of a spring. You can imagine I'm this spring all coiled up, and then I uncoil like this. And while I'm uncoiling like this, what I'm doing is my hand is pushing to the left on the cannonball, but what's my foot doing? It's pushing to the right on the boat, okay? And to make things as simple as possible, I'm this complicated sort of uncoiling spring that has mass. But I can get rid of my mass. So let's suppose that my mass is negligible compared to the mass of the cannonballs, etc. So just as the simplest possible model, and this is a really good skill in physics, can you find a simpler model that captures all of the essential physics? And that simpler model is a compressed spring. And when I let that compressed spring uncompress, well, that's my hand pushing on the cannonball, and that's my foot pushing on the rest of the boat, on the boat and the rest of the cannonballs. And I will assume, for simplicity, without losing any of the essential physics, that that spring is massless. Now, there's an important aspect to this spring. This spring stores energy when it's compressed. So there's some energy stored in that spring. And so at the end of the day, after that spring compresses, or uncompresses, after I've done this, right, then this guy has some kinetic, it's moving this way, has some kinetic energy. This guy's moving this way, has some kinetic energy. That's energy. Where did that energy come from? Well, it came from this force acting through this displacement, this force acting through this displacement. That was how the energy was transferred to these two objects. But where did it come from? Well, conservation of energy says it came from the energy that was originally stored in the spring, which would be like chemical energy for me. Okay, but I'm a much more complicated system. When I do this, sure, I'm using chemical energy. Chemical energy is being converted through this, through work, energy transfer mechanism, to kinetic energy of these two objects that I'm pushing against like this. Okay, great. But also, there's thermal energy. I heat up, okay, because I'm inefficient. All right, so this system is much more complicated. So this is the basic system of how I would propel my boat to the shore. Now let's think about this in a little bit of detail here. So, so first of all, we know that the spring, when it's compressed, is exerting some force. This is my hand, is exerting some force to the left on the cannonball, and there's an exactly equal magnitude force opposite direction that my feet are exerting on the boat and the rest of the cannonballs. Okay, so we have that force. Those forces are equal. We know that F equals ma, so this force will equal the mass of the cannonball times the acceleration of the cannonball to the left. And that must equal this force, which is equal to the mass of the boat and the rest of the cannonballs, times the acceleration, call it capital A, of the boat and the cannonballs to the right. And so you see, because big M is, say, much bigger than little m, you can see that for whatever acceleration the boat has to the right, there will be a much greater acceleration of the cannonball to the left. And so we'll draw the accelerations as sort of curly, squiggly vectors. Okay, so when you apply equal forces on unequal mass objects, the lower mass object will accelerate more. There's a lot of acceleration of the cannonball to the left, high acceleration, whereas there's a low acceleration of the boat and the rest of the cannonballs to the right. So we got that. Okay, so that's thinking about it a little bit from the point of view of dynamics. And then we say, oh, okay, but now the time over which we are pushing, we have an acceleration. An acceleration represents a changing velocity. Okay, and so that velocity changes over a certain amount of time. Well, the time that I'm pushing on that cannonball with my hands and on the boat with my feet. And so it's a large acceleration happening for some given amount of time, and so the velocity of the cannonball to the left will be large. Okay. Lower acceleration for the same amount of time will mean that the change in velocity of the boat and the cannonballs to the right will be smaller. So let's call that big V, and it's smaller in magnitude. So we have the cannonball flying off fast to the left, and the boat and the rest of the cannonballs having gained a small velocity to the right, towards the shore, where we want to go. Okay, so this whole thing is, from the point of view of dynamics, we thought a little bit about dynamics, F equals ma. We thought a little bit about kinematics. Okay, so an acceleration represents a change in velocity. Okay, and now we can think about this in terms of momentum. Okay, so what we have is the momentum of, what do I want to show first? Okay, so the momentum of the cannonball to the left, Newtonian definition of momentum is mass times the velocity. So it'll be a small mass times a large velocity to the left. And we know that at the end of the day, we started off with a system that was at rest. There was no quantity of motion. The total momentum was equal to 0. Afterwards, by momentum conservation, we know, because this is an isolated system, we'll imagine there's 0 friction between the boat and the water. It's just an isolated system. Okay, we know that the total momentum has to stay 0. So if the cannonball gained a momentum little m, little v to the left, then the boat and the rest of the cannonballs must have gained a momentum big M, big V to the right, which is equal in magnitude. So the total momentum remains 0. So there was some momentum transferred to the cannonball to the left, and there was an equal and opposite transfer of momentum to the boat and the rest of the cannonballs to the right. Okay, and so m times v, take a small mass times a large velocity. Maybe that gives you something that looks like this. That is equal to a large mass times a small velocity. Okay, so remember, in physics, in nature cares certainly more about the momentum than it does about the velocity of the object, the quantity of the motion. It's the mass-weighted velocity that counts. Okay, so the momentum of the cannonball to the left equals the momentum of the cannonball to the right in magnitude. And so we can think of this as, well, how did this momentum get transferred? Well, the momentum got transferred because how do you transfer momentum? Well, you apply a force over time. So I applied the force of my hand over time on that cannonball, and that transferred momentum to the left to that cannonball. But my feet at the same time was transferring exactly the same force to the boat and the rest of the cannonballs over time. It's just the force over time. Same force, same time, same momentum transferred in that direction as in that direction. Okay, so these two momenta are of equal magnitude, opposite directions. So this is sort of thinking about this from the point of view of either momentum transfer or momentum storage. Total momentum stored was 0 to begin with. Total momentum stored at the end of this throwing the cannonball is also equal to 0. Now, we can also think about it in terms of energy. Okay, so remember that a force acting over time transfers momentum. A force acting over displacement transfers energy, and that's where this energy in the spring comes from. Okay, so what we've got is, remember that these two forces are equal in magnitude. So acting on the cannonball, we have a force F to the left, and we have a force F to the right. And so that force is acting over some displacement. Okay, so this displacement is this long. Okay, so because we know that the acceleration of the cannonball is larger, the final velocity of the cannonball is larger, basic kinematics tells you that the displacement of the cannonball is going to be more, it's going to be large. So this is the displacement of the cannonball. Let's call that little d. This is F. So the cannonball displaces a great distance to the left. At the same time, while that's happening, we have the boat and the rest of the cannonballs has a smaller acceleration, a smaller final velocity. Its displacement to the right, while I'm doing this, is going to be less. It'll be smaller. So it'll be like that. And then, the simplest idea is, work is force times distance, actually the integral of force, F dot dr. But when the force is constant, and let's just imagine it's, say, roughly constant, we just go force times distance. Okay, so same force times larger distance means that there has been more kinetic energy transferred to this guy than this guy. This is same force over smaller displacement. Okay, and so we say the change in the kinetic energy of little m, which we'll call delta little k, that transfer of energy through work, force acting over displacement, will be greater than the amount of kinetic energy transferred to the big M, which is delta big K. Okay, so that's good. And then we say, okay, well, regardless, this guy gained some kinetic energy, this guy gained some kinetic energy. The kinetic energy in the system went up, so some energy elsewhere had to go down because energy is strictly conserved. And where did it come from? Well, what went down is the energy in the spring as it uncompressed. And so we can just read off, we can immediately say, well, the energy in the spring, well, that's equal to the change in the kinetic energy of little m plus the change in the kinetic energy of big M. Okay? And so, so that's an important consideration here, because now this sort of ties into rockets, right? So instead of having a spring that's uncoiling like this and throwing massed cannonballs to the left, with a rocket, what we're doing is we've got this rocket and it's throwing stuff out as well. And that stuff it's throwing out is exhaust gas particles. So a rocket is something that has propellant in it. The majority of the mass of the rocket, when you first, on the launch pad or whatever, is 90 or 95% of that mass is propellant, so fuel and oxidizer. And so a good example of a fuel and oxidizer is hydrogen and oxygen. And so when you burn hydrogen and oxygen, what you get is water molecules. Okay, so with a hydrogen liquid oxygen rocket, the exhaust gas coming out is water molecules, super hot, so they're vapor, so it's steam. Okay, so a rocket is like the kind of a fancy, interesting kind of a big steam engine. Okay, thermodynamic kind of steam engine. Anyway, so the energy here, so what we're thinking about is when the hydrogen and the oxygen burn, they chemically combine together, then there's some rearrangement of the electrons, and the energy stored in the electrostatic field goes down. It's a lower energy bond, and so then there's energy released. Well, what form does it take? Well, it takes the form of kinetic energy, and so those exhaust gas particles are coming out really fast. And so the kinetic energy of the exhaust gas particles plus the kinetic energy that's going into the remainder of the rocket, that energy increase is coming from the chemical energy that's stored in the hydrogen and the oxygen and is released when you burn. Okay, so that's the basic idea. So in the case of a rocket, we're really talking about chemical energy, which of course we know is really electrostatic field energy. In the case of me, in the boat with the cannonballs, well, that's also chemical energy. And then we need extra chemical energy because I'm inefficient with thermal energy, et cetera, et cetera. Okay, so this is sort of an intuitive understanding of how a rocket works. The basic idea is if you're floating out there in the middle of empty space and there's nothing to push against, you have to take a chunk of yourself, a chunk of your mass, and throw it out the back using some form of energy to accelerate it, to give kinetic energy, and that's chemical energy of chemical reactions, or it's nuclear energy or whatever. Okay, so that's that. So let's talk a little now about rocket propulsion sort of more formally. We will sort of apply conservation of momentum more formally, and we'll do some math, and we'll discover some interesting things. Okay, so the first picture we're going to draw here is our rocket. So we're floating out in the middle of empty space. There are no forces, external forces acting on the rocket or the exhaust gas particles or anything. There's no planets around exerting gravitational forces. We just have this rocket out in the middle of empty space. And the length of this rocket is going to indicate the amount of mass that's in that rocket. Remember, a rocket starts out 90-95% propellant. That's the majority of the mass. And then there's some metal the rest of the rocket is some metal containers for the propellant and people. There's people inside here and stuff like that. But the most of the mass of the rocket is propellant. Okay, and so we'll suppose that at this instant of time, the amount of mass of the rocket, mainly propellant, is m. And the rocket is moving with the speed v. So speed v relative to what? Velocity relative to what? Well, we'll pick an inertial reference frame. And we'll stick with this inertial reference frame. Okay, so relative to this inertial reference frame, we see a rocket at this instant of time with mass m and velocity v to the right. Now, it could have been that this rocket started with velocity 0 and was, firing and spitting out exhaust gas particles and, coming up to a speed v and so on. We don't care about those exhaust gas particles now. We're going to cut those all out of our system, and we're going to say our system consists of the rocket and of all its propellant at this instant of time. You have this chunk of mass moving with velocity v to the right. This system is isolated. Okay, so we're not going to allow any momentum in or out. It's isolated, which tells you that the change in the total momentum in this isolated system, which is rocket moving forward, or the rest of rocket moving forward, plus any new exhaust gas particles we throw at the back, that the change in the total momentum of rocket and exhaust gas particles must equal 0. Okay, so what is the total momentum to begin with? What's the total momentum initial? Well, it's just the mass times the velocity. So P total, let me draw it as a vector down here. So P total initial is equal to mass of the rocket at that initial time times the velocity. And that's a vector to the right, which we'll draw as being that long. So that's the quantity of motion that you have. Because the system is isolated, that quantity of motion can never change. All right, so now what we want to do is we want to think a little bit about this. Okay, so we're going to take a chunk of mass of the rocket. We're going to take some propellant and oxygen, some fuel and oxygen, which were initially at rest with respect to the rocket. We're going to burn them together. And at the end of the day, we're going to create a bunch of exhaust gas particles, water molecule particles, which at the end of the day are moving fast, coming out of the back of the rocket. Okay, so during a time delta t, this is important. So this is the delta t is the time in which I'm pushing on that cannonball. Delta t is the time that we're going to allow some fuel and oxidizer to burn. And during that time, effectively what's happening is we have this rocket, which was originally this long. We're going to take a chunk of that rocket mass and throw it out the back. Okay, just like we took a chunk of the mass of the boat plus cannonballs and threw it out the back. Okay, so this is the little chunk this is our little cannonball going out the back. It's the chunk of exhaust gas particles that we are accelerating out back the rocket. And so the mass that's left in the rocket is now less, so we'll draw a shorter rocket. And so it looks like that. So we will suppose that the chunk of mass of exhaust gas particles has mass epsilon. And in physics, often we use epsilon to denote a small quantity. Maybe this is 1 gram compared to thousands of kilograms of the rest of the rocket. But the rest of the rocket, nevertheless, does decrease in mass. By how much? Well, by epsilon. So the mass of if the mass of the rocket was m here, then the mass of the rocket at this point is m minus epsilon. Okay, so it looks like that. And we will call the chunk of exhaust gas particles that are being thrown out to the left, we will call that subsystem 1, and we'll call the rest of the rocket subsystem 2. So it looks like that. And then the idea is this spring, when you let a spring uncompress, well, while it's uncompressing, it's exerting a force of some magnitude to the left and an equal and opposite force to the right. And so we will represent this as a force acting on those water molecules, those exhaust gas particles, which started initially at rest with respect to the rocket. So the rocket's moving like this. That fuel and oxidizer were initially at rest. Later on, they ended up moving that way. They combined together to form water and are moving that way. Okay, so there is a force on 1 due to 2, which is that way. That's my hand pushing on the cannonball. And then there's, by Newton's second law, an equal and opposite force onto the rest of the rocket due to number 1. Okay, and so that's really just me pushing my feet, pushing on the boat that way. Okay, so we have that situation. And then we can think about this as momentum transfer. Now, how do you transfer momentum? Well, you have a force acting over time. Here we had the force of my hand applied to the cannonball acting over time, which gave this this amount of momentum transfer. So this is, let's call this negative I, and this one positive I. Okay, so let's actually talk about this one first. Okay, so what we've got is there's a force on the rest of the rocket due to the exhaust gas particles, effectively. That force times this time interval delta t that we're letting this burn happen. So that force times that time is a momentum transferred to the rest of the rocket, the thing of mass m minus epsilon. So that is I, and that is transfer of momentum from system 1 to subsystem 1 to subsystem 2. So this is I, and it's transfer of momentum from 1 to 2. And at the same time, while that's going on, we have a force acting on number 1, the exhaust gas particles, which acts over time t. How do you transfer momentum? Force acting over time. And so because F21 and F12 are the negatives of each other, this transfer of momentum to the exhaust gas particles is negative I. Okay, so that's the transfer of momentum from the remainder of the rocket to the exhaust gas particles. And so you'll see there's momentum transferred this way and this way. So, how should I say this? So momentum basically came from this system. An amount of momentum I in that direction was transferred from this system to this system. So the amount of momentum, the amount of forward momentum that fuel and oxidizer used to have when it was at rest with respect to the rocket, now gets a certain amount of forward momentum was removed from that. And in fact, so much forward momentum was removed that it actually comes out with backwards momentum. Okay? And then that momentum in that direction was just transferred from those propellants, gets transferred to the remainder of the rocket. So there's momentum I transferred from here to here, from 1 to 2. Okay? So, yep. So that's thinking about momentum conservation in terms of transfer. This whole thing happens during a time delta t. Okay? And then we come to, at the end of this time interval delta t, our situation now looks like this. We've got the remainder of the rocket, which is now this long. It's less mass. Okay, and we hope that its velocity is greater than v. Okay, so, and it will be. So this vector v here is longer. So this is v plus delta v now. And there's a chunk of exhaust gas particles now moving to the left, at least initially when the speed of the rocket is slow. So now this is a crucial point, a little point to pay attention to here. So our system now consists of the remainder of the rocket of mass m minus epsilon, moving to the right with a velocity v plus delta v, and this chunk of exhaust gas particles. The question is, we know it's mass, but how fast is it moving? Well, so this is important. We're going to say that VE, that's the speed of the exhaust gas particles. So VE equals speed, so it's a positive number, speed of exhaust gas particles as seen from the rocket. Okay, so there's someone standing on the back of the rocket here. That rocket is accelerating like this. They're in this accelerating reference frame. Doesn't matter. They're standing at rest with respect to the rocket, and they see exhaust gas particles, flying away from the back of the rocket with a speed VE relative to the rocket at rest. Okay, so if the rocket were at rest, then the speed of those exhaust gas particles to the left would just be VE. However, these exhaust gas particles are being thrown out not from an object at rest, but an object with a velocity v. Okay, and so the velocity of this guy, the speed of this guy to the left is VE, but they're being thrown off of an object that's moving to the right with a speed V. And so the speed of this chunk of exhaust gas particles to the left is not VE, it's a little bit less than VE. So the speed to the left of this of that chunk is VE minus V. This is a velocity to the left. Okay, so when the speed of the rocket is 0, then the velocity to the left is a positive VE. Okay, and as the rocket picks up speed, moves faster and faster and faster, those exhaust gas particles relative to our original inertial reference frame, they are moving less fast all the time, okay, to the left. Okay, very good. Yeah, and actually this is a really important point because we're going to discover, of course, that a rocket can go faster than the exhaust gas particles you're throwing out. Okay, so typically exhaust gas particles for a chemical rocket is about 4 kilometers per second. Okay, whereas you can get a rocket going, well, at least 11 kilometers per second. That's the escape velocity from the surface of the Earth, right? And so rockets can move faster than their escape gas particles moving out the back. So there will come a time where the rocket is moving faster than the escape gas velocity, and these exhaust gas particles, they're actually, relative to the original inertial reference frame, are not moving to the left. They're actually moving to the right. So that's a really interesting point that we're going to come across later. Okay, so right, so let's suppose that so we know that conservation of momentum says that for an isolated system, the total momentum can't change. So the initial momentum inside our isolated system was m times v. Well, the final momentum of that thing and that thing must also equal m times v. So we have a vector of exactly the same length, which is p total final. Okay, now that p total final is composed of two pieces now. So when the rocket, at least when the rocket is moving less than the speed VE, those exhaust gas particles, they will have some momentum to the left. So the contribution to the total momentum of the exhaust gas particles is a little vector to the left. Well, then what's the momentum of the rocket to the right? Well, it must be equal to the total momentum plus this. So this little extra bit of momentum of the rocket to the right is compensated for by the little bit of momentum of those exhaust gas particles to the left, so that the momentum of the rocket to the right, this one, plus the momentum of the exhaust gas particles to the left, is actually the original momentum of the rocket. So it's the same. So P total final is equal to P total initial. Okay? Great. So I think that's basically it. So now let's do some math. Let's come up with an important equation called the rocket equation. All right. So let's see. Do I have enough room to do this? Maybe. Okay, so we apply conservation of momentum in the form of the momentum of an isolated system never changes. So 0 is equal to the change in the total momentum. And in this case, it's all the momentum is just in the positive x direction, and so we can just drop the vectors and just deal with the x components of this. So delta P total is equal to 0. So that's P total final. Sorry, without the vector. P total final, the x component, minus P total initial. So let's see. Yeah, we might be able to fit this here. Okay, so P total final, there's two things. So let's put this in square brackets. What we've got is an object moving with an object of mass m minus epsilon, moving with velocity v plus delta v. Okay, so the momentum is mass times velocity. So we have an object of mass m minus epsilon, moving with velocity v plus delta v. Okay, great. And then we add to that the momentum of this guy. Okay, and so we would go the mass of this guy, which is epsilon, times its velocity to the right. Okay, or we could say minus the mass of that object times its velocity to the left. That's maybe a little intuitively clearer. Its velocity to the left is VE, basically how fast these things are being spit out the back of the rocket, minus the speed of the rocket to the right. That gives the velocity to the left. And so we say there's a left component of momentum, which is the mass of the object times the left velocity, which is VE minus V. Okay, and so you can, VE minus V. And so you can see when the speed of the rocket is small, let's say it starts off 0, then this contribution to the momentum is negative. Okay? Signs are really important. So that's the momentum, the total momentum in our final situation. And now we have to subtract. Yeah, sorry, that's P total final. And now we subtract P total initial. And P total initial is easy. It's just the mass of the rocket at the original time, T initial, times V. So minus mv. So that's easy. Okay, and so now we just crank this out. So we have m times v plus m times delta v, okay, minus epsilon times v minus epsilon times delta v. And then there's a minus epsilon times VE, and then there's a positive epsilon times V, and then there's finally a minus MV. Okay, looks like a whole bunch of terms, big mess, but what we can see is there's lots of cancellations. So this positive MV cancels that minus MV, great. And there's a positive epsilon V and a minus epsilon V, so those things cancel. So we went from a whole bunch of terms down to, what do we have left? 1, 2, 3 terms. Okay? But now here's a super important point, which sometimes causes some confusion. So let me try to explain this clearly. The point is that these two terms, or let's say this term is negligible in size compared to these two terms and can be ignored. And so why is that? Well, so this term delta v, the change in velocity, is the acceleration times the change in time. Okay, and so the change in velocity is proportional to the change in time. Under a given acceleration, if you double the time, you allow that acceleration to happen, you double the change in velocity. So this delta v, so this whole term is proportional to delta t, this short time interval over which we are allowing this burn to happen. Okay, this term over here, that epsilon is the amount of mass that you're throwing out of the rocket during a time delta t. During, say, 1 second, you throw 100 kilograms out. During 2 seconds, you throw 200 kilograms out. So this epsilon, the amount of mass that you're throwing out the back during that time interval delta t, is also proportional to delta t. Okay? But now you look, but what about this guy? Epsilon is proportional to delta t, and delta v is also proportional to delta t. So this term over here is of second order. Okay, it's smaller. This is proportional to delta t squared. So if delta t is like a small time interval, like a 1 over 1,000, 1,000th of a second, then this thing will be proportional to 1 millionth. Okay, so 1 millionth is way smaller than 1 over 1,000. And so this term can be neglected. And certainly in the calculus limit that delta t goes to 0, this term is utterly 0 compared to these two terms. You only need to retain the terms linear in delta t. Okay? And so all we have left is just these two terms, this one and this one. So this whole complicated thing reduces to something very simple. Okay, and so what we have is that m delta v, I want to write this, m delta v, okay, minus epsilon VE is equal to 0. So let's stick the epsilon VE to the right-hand side. It's equal to epsilon VE. And now, what is epsilon? So we know that epsilon is related to the change in the mass of the rocket. So the mass of the rocket started out as m over here. The mass of the rocket here is m minus epsilon. So the change in the mass of the rocket during this time that you were throwing exhaust gas particles out is negative. The mass of the rocket went down. By how much did it go down? Well, the positive epsilon. So delta m is negative epsilon. Okay, so the the mass of the rocket changed, it went down. The change in mass is negative. How much is it? Well, it's negative epsilon. Okay, so epsilon is the same as negative delta m. So this is negative, let's write down the VE first, times delta m. So we have m delta V is negative VE delta m. Okay, and then we're going to take the calculus limit here, where delta t goes to a dt, a differential, and delta v goes to dv, and delta m goes to dm. Okay, and so we can write this as, take this equation and divide both sides by m. And so we can write this nicely as dv is equal to, dividing by m here, is equal to negative VE times dm divided by m. Okay, so that's our basic sort of calculus result. It says that during an infinitesimal amount of time dt, the change in the velocity of the rocket dv is equal to negative the speed of the exhaust gas particles, a positive number, times the change in the mass of the rocket, which is a negative number, divided by the mass of the rocket. So the increment, the fractional change in the mass of the rocket. Okay, and before we actually going to run out of room here. Okay, so let me just record one result here, and I'll put it up here because we're going to need this later when we come to this side of the board here. So I'm going to take this important result here, okay, expressed in differential form. I got that important result. I'm going to divide both sides by dt. And so this important result says that dv divided by dt, which is actually the acceleration of the rocket, the rate at which the velocity of the rocket is changing, that's equal to negative VE over m times dm dt. Okay, so this is an important result which we're going to use later. Okay, and so it says that the acceleration of the rocket is proportional to dm dt. dm dt is the rate at which you are throwing mass out. Remember, the crucial thing about how a rocket works is you have to throw mass out the back. You have to take the mass that's in your boat, which is cannonballs, and throw them out the back. So there's a rate at which you are throwing mass out the back. There's a rate at which these exhaust gas particles, that steam, those water molecules, or kilograms per second, is going out the back. So in order to accelerate the rocket, you need a high rate of flow of just mass out the back of the rocket. And, you know, say for a Saturn V rocket, it was ridiculous. It was like, I think it was like something like 2.5 tons of propellant per second was being thrown out the back. Okay, and then times VE. VE is important, how fast you can throw those particles. So how strong the chemical reaction is to get those exhaust gas particles moving as fast as possible. Okay, so we got that. And then let's do one final thing with this. Let's see if we can fit this in. We're not going to be able to fit this in here. Okay, so let's just go over here. Just getting a little too messy. Too small down there. All right, very good. Lost my little tip of the pen here. Let's flip that around. Okay, so it's like that, and so let's just take sort of one step over here for this. And so then what we do is we take this equation and we integrate both sides. And so we take dv and we integrate that. The integration variable is the speed, the velocity. We'll go from v initial to v final. And on the right-hand side, we're going to have a negative. We're going to assume, just for simplicity, that VE is constant. Okay, so let's assume that VE is constant, which means, and is a reasonable assumption, what it's saying is that when you're standing on the back of the rocket, as that rocket is firing, you're throwing out exhaust gas particles with some speed VE relative to the rocket. And that's not going to change because it's the same chemistry involved, right? It's like hydrogen and oxygen burning, and so they're going to be coming out at a roughly constant velocity. Okay, so we'll assume that that's constant, so we can pull it outside of the integral, which is VE, times the integral of dm divided by m. Okay, and the integration variable here is m, so we're going to be integrating that from the initial mass of the rocket, whatever it had, say, a long time ago at launch, to the final mass of the rocket, any final time that we choose. And usually it's the time when all the propellant is burned out. Okay? And then, if you know a little bit of calculus, you know that the integral of 1 over x is log x, natural log of x. The integral of 1 over m is natural log of m. So this is negative VE times the natural log of m, evaluated at m final minus m initial. So it's the log of m final minus the log of m initial. But the log of a minus the log of b is the log of a over b. Okay, so this is the log of m final divided by m initial. And so one final step here, and this little bit of space left here, is to say, well, this is, on the left-hand side here, this is equal to the change in the velocity. No, let's put it up here. So on the left-hand side of this equation, we have the integral of dv. That's add up all the little incremental changes in the velocity of the rocket as it's speeding up. And so that's equal to delta v. So the delta v of the rocket, this is standard terminology, delta v of the rocket is v final minus v initial. Okay, that's equal to, on the right-hand side, this thing, negative VE log m final over m initial. Now, the delta V of the rocket is a positive thing, right? We want the rocket to speed up. So the change in the rocket is velocity is positive, but there's a negative sign over here. So that makes this form of the equation awkward. But you know that the log of a divided by b is the negative of the log of b divided by a. So to get rid of that minus sign and turn it into a positive sign, we just need to just flip m final over m initial and have it m initial divided by m final. Okay, so this becomes VE, positive VE, times the log of m initial divided by m final. Okay, so this is the rocket equation. And it's a very general result. The only assumption that we made in this is that VE is equal to constant, which is a very reasonable assumption. And if you don't make that assumption, well, then you're just left with this ugly integral. Okay, and so for most practical considerations, this is good. It allows us to do a lot, to understand a lot about how rockets work. Okay, so now the thing is, at the end of the day, what we want to do is we want to maximize delta V, right? That's the whole point, is to get a rocket going fast, right? You need it to be fast enough to have escape velocity from, you know, this planet or that or whatever. So you want to maximize that delta V, the change in velocity of the rocket. So there's two ways to do that. So one way is you want to maximize VE. Okay, so then this becomes a question of chemistry. If you're using chemical rockets, you know, there's also nuclear rockets, there's also matter, antimatter rockets, and whatever. But with chemical rockets, you know, this is a question of chemistry. So when you take some fuel and some oxidizer and you let them burn, you know, how much energy is released, which can be converted into kinetic energy. And, you know, for that amount of energy released, what you want is the speed to be large. So suppose that a given chemical reaction results in a certain amount of energy being converted into kinetic energy. Well, you know that the kinetic energy is, you know, 1/2 mv squared. So the smaller you, so for a given kinetic energy, the smaller you make m, the mass of the exhaust gas particles, the greater the speed of the exhaust gas particles will be. And so you have to think about things like, well, I got some chemical reaction, but I want my exhaust gas particles to have really, really small mass. That's why hydrogen and liquid oxygen are great, because, two of those three things, H2O, is hydrogen, which is super light. Okay? So anyways, that's why hydrogen and oxygen are really good as a fuel, really quite efficient. So typically with chemical rockets, the maximum that you can get is something on the order of magnitude, a little squiggly line, on the order of magnitude of about 4 kilometers per second. Okay? So I want you to think about that number for a second. The escape velocity from the surface of the Earth is 11 kilometers per second. To get to the moon, we have to be moving at 11 kilometers per second, which is faster than we can throw those water molecules out the back of the Saturn V rocket. So clearly we can get rockets moving faster than the speed of the exhaust gas particles. And that's going to come up really important in a couple minutes. The second thing we want to do to maximize the change in velocity of the rocket, the delta V of the rocket, is to maximize. Now the logarithmic function is a monotonically increasing function. Okay, and so what we want to do is we want to maximize the ratio of the initial mass of the rocket to the final mass of the rocket. Remember that the initial mass of the rocket is all of the metal and people and stuff in the rockets, plus the propellant, which is fuel and oxidizer. That's the initial mass. The final mass is when you've thrown out all that propellant, fuel and oxidizer, which is like something like 95% of the mass, and all you're left with is this empty shell of metal. Okay? And people and stuff like that. So you want to maximize this, which means, maximize that ratio, which means essentially a lot of fuel. So it's lots of propellant and little payload. Little, payload is the stuff you eventually get moving really fast. What's left of the rocket. This thing gets smaller and smaller and smaller. Only left with is that little thing. Okay, so let's give an example here, just a representative example, and you'll see how sort of dramatic this whole thing is and why it's hard to build rockets to get to the moon or Mars. Okay, so suppose we want delta V to be, say, 11 kilometers per second. So that's just starting at rest out in the middle of empty space, and you want to accelerate this rocket up to 11 kilometers per second, which is, say, the escape velocity, from the surface of the Earth. So it's a good representative number for the kinds of delta V's you need rockets to have. Okay, so something like that. And so what does that tell you? Okay, so that tells you you have 11 kilometers per second is equal to, that's the delta V, is equal to VE. Suppose that we're using a typical value of VE, typical largest value possible, is 4 kilometers per second, times the log of m initial over m final. Okay, so I will let you do this calculation. So you solve for m initial over m final, and what do you get? So m initial over m final is the exponential of 11 divided by 4, which is around 16. It's approximately 16. Okay, so what that means in terms of your rocket here, if we draw our rocket, this is our rocket sitting on the launch pad, and let's suppose that this is the chunk of rocket that's going to be left, and this represents all of the propellant that we're going to throw out. So what it means is that 15 parts of propellant for every 1 part of payload. So if the mass of what you want to get going is, say, 1, then the mass of the propellant has to be 15. So that the initial mass is the total, is the propellant plus the final payload, the final thing you get moving fast, 15 plus 1 is 16, divided by mass final is 1. Okay, so this is what it looks like. So that's why rockets, of course, are so huge. Okay, and it's a real problem. This is just like in empty space without any gravity. To get it up to 11 kilometers per second, you need something that looks like that. Okay, and so now it's even worse if you're starting on the surface of the Earth and have to fight against gravity. And so really what happens is rockets are divided into stages. And if you think really carefully about it, as say NASA engineers did, they realized, yes, for the Saturn V to get to the moon, we're going to need 3 stages. And so dropping off a stage means you're dropping off a lot of extra mass, useless mass, after the propellant in this chunk has gone away, while the metal that's made of, like the extra tanks and all that stuff, well, just jettison those. These are now gone from the picture and then start again. Okay, with a rocket with all of that excess baggage thrown away. And so you have rockets that are staged, et cetera, et cetera. Okay, great. So now I want to point out one of the most interesting aspects of this whole thing. So we're going to suppose that, and that has to do with this idea. What happens, because these exhaust gas particles are moving to the left with the speed VE minus V. But as the rocket picks up speed, and it can certainly pick up speed to larger than VE, those exhaust gas particles, they're spit out, certainly moving to the left relative to the rocket, but they're moving to the right relative to our original inertial reference frame. So that results in something very interesting, a very interesting phenomenon. Okay, so when we start off, let's suppose that V initial is equal to 0. The rocket starts off at rest, and we are in this inertial reference frame. And then the first parcel of exhaust gas particles that is thrown to the left has a velocity, has a large velocity v to the left. So here's our chunk of exhaust gas particles, large velocity VE to the left. Okay, and then the rocket picks up a little bit of speed. Okay, and then in the next moment of time, we throw out another chunk of exhaust gas particles. And because the rocket now has some velocity to the right, those exhaust gas particles come out with the speed VE relative to the rocket. But because they're being emitted from an object that's moving to the right, then the velocity to the right relative to the original inertial reference frame is less. And so the exhaust gas particles come off. The next set of exhaust gas particles come off with a smaller velocity to the left. Okay, so, and then this keeps going. As the rocket picks up speed, the exhaust gas particles, their velocity relative to the original reference frame is getting lower and lower. There is a point at which, when the speed of the rocket, v, is equal to the speed of the exhaust gas particles, say 4 kilometers per second, then the exhaust gas particles that are emitted at that time, they're moving with a speed ve relative to the rocket, but the rocket's moving with speed ve, so they come out at rest relative to the original inertial reference frame. Okay, so this side of the diagram is speed v less than ve. This is speed v equal to ve, and then afterwards the rocket keeps speeding up and up and up. The speed always increases. Okay, so now the rocket is a little bit later. The rocket is moving even faster to the right. It's moving faster to the right than the exhaust gas particles are being thrown to the left. And so these exhaust gas particles, when they are released from the rocket, they're actually moving to the right relative to our original inertial reference frame. And this keeps on happening, and the velocity of them to the right gets larger and larger. And then so finally, at the end of the day, we are left with just the payload of the rocket. All of the exhaust gas particles have been emitted. And so we have this guy has V final. So V final is certainly bigger. Well, in fact, let me not put that there. Let's just say this is V final, which is a large velocity to the right. And this whole side of the diagram applies for the case the velocity of the rocket is greater than the escape gas speed. Okay, so we have that. Now here is the crucial point here. The crucial point is that when we think of this in terms of conservation of total momentum, or conservation momentum, thought of as the total momentum of an isolated system, this whole thing is an isolated system. Okay, and so when you are at this point, suppose this rocket starts at rest. The rocket starts at rest, the total momentum in the system is 0, and it will always remain 0. Okay, so the total momentum of all this junk in motion is equal to 0. But you'll notice that when you start getting to this time on this side of the diagram, you'll notice that the momentum of those chunks of exhaust gas are no longer to the left, they're actually to the right. And so the exhaust gas particles are actually adding momentum to the right, which means that the momentum of what's left of the rocket has to be changing to the left, has to be getting smaller and smaller and smaller. So the momentum of the rocket starts off at 0. It starts picking up speed. Great. Momentum increases, increases, increases. It's at this point where the momentum is maximum. So P is equal to maximum. Okay. And let's put this V final as V maximum. Okay, so the momentum is maximum at this point for the rocket itself. Okay, because later on, for all later times, the momentum that the exhaust gas particles adds to the system is to the right. And so the momentum of the remainder of the rocket must be decreasing all the time. Okay, and so that's kind of an interesting point. So let's look at that in let's look at that in a little bit of detail. So the momentum of the rocket is mass times velocity. So let's actually look at how that changes with time. So this is going to be the rocket thrust equation that we're going to get from this. Okay, so dp dt. So we're saying P here is not the momentum of the exhaust gas particles, it's only the momentum of the rocket, what's left of the rocket. Okay, so dp dt, what does that mean? Well, it means to take the time derivative of the mass of the rocket at any instant of time. And remember, the mass of the rocket is going down because we're throwing chunks of the rocket out the back. So mass times the velocity of the rocket at that instant of time. So this total change, when we're over on this side here, the momentum must be decreasing. dp dt must be negative over here. Okay, and so what's happening is, yeah, the velocity is always going up, okay, but the mass is going down, greater, such that, the time derivative of that whole thing is negative. So let's work this out. M and V are both functions of time. So it's the time derivative of a product. So let's write that as V times the time derivative of M plus M times the time derivative of V. Okay, so what are these things? So dm dt is the rate at which the mass of the rocket is changing, okay, which is of course a negative. The mass of the rocket is going down. It's the mass flow rate. It's the number of kilograms per second of propellant in the form of exhaust gas particles now that's being dumped out the back, water vapor that's being dumped out the back of, say, a liquid hydrogen, liquid oxygen rocket. Okay? And dv dt is, of course, the acceleration of the remainder of the rocket. Okay, so now what we're going to do is we're going to use this equation. We have an expression for dv dt. Let's take that expression and plug it in for here. So we get a, just want to keep this as short and simple as possible. So we have a v dm dt, which is what we had before, plus m times dv dt. So m times this thing, there's an m here, there's an m here, it cancels. It's negative ve dm dt. Negative ve dm dt. Okay, so this is nice. So the rate of change of the momentum of the rocket is dm dt, that's the common factor, times v minus ve. And so this is v minus ve times dm dt. And now dm dt is a negative number, and so we can deal with it. It's always strictly a negative number, so we can deal with that, make this equation a little bit easier to follow. We can take the v minus ve, flip that around. So this is the same as ve minus v times the magnitude of dm dt. Okay? Times the magnitude of dm dt. Okay, so now that's interesting. So this is dp dt. Yeah, again, we're going to run out of room here. Okay, so so this is an important result. Let's circle this one, dp dt, and talk about that for a second. Okay, so this thing, dm dt, magnitude, that's the number of kilograms per second of mass you're throwing out the back. You know, how many, if my cannonball is 1 kilogram, it's how many cannonballs per second I'm throwing out the back of my, my boat. Okay, so that's dm dt. Like I said, for like a Saturn V, it was, I can't remember the exact numbers, 2.5 tons of mass per second going out the back. It was ridiculous. Times ve minus v. So you can see that when the speed of the rocket is small, like initially, then this term is positive, and dp dt, the momentum is increasing. Okay, dp dt is positive, the momentum is increasing. That's for this half of our diagram here. But then when the speed v of the rocket exceeds the speed of the escape gas particles, then this term becomes negative. And so dp dt is negative, which means that the momentum is going down. Okay, so this thing here is the mass flow rate, or the burn rate. I mean, this is liquid hydrogen, liquid oxygen. They have super powerful pumps, which pump this massive fluid at super high rates, super high number of kilograms per second. Like it's, like I said, it's crazy. Okay, so now let's actually want to elaborate on this a little bit. So we're going to need a little bit of room here. Let's just take this whole side here. Because this is a really interesting point about the rocket, a really interesting illustration of, the meaning of momentum conservation, how it all works. Okay, so in fact, let me just sort of shift. Well, actually, first I'll do this. First I'll say, okay, great. So there's this idea of the thrust of the rocket first. So the thrust of the rocket. So what does that mean? So it's the effective force acting on the rocket. So force equals mass times acceleration. So the way we will write this is we will say, we have, I should say this a little bit differently. We have the mass of the rocket at any instant of time times its acceleration, which is dv dt. Okay? So this has the dimensions of force, and so we will call this mass of the rocket at any instant of time times its acceleration at that instant of time. We will call that the effective thrust force. Okay, that's the effective force that the this chemical reaction and throwing out these particles at the back is exerting on the rest of the rocket. Okay, thrust force. That's called thrust force. And so this dv dt is equal to, if we just look back, we had dp dt is, well, here we have it. We're looking at m times dv dt. So m times dv dt is equal to, how do I want to write this? Yeah, dp dt minus this term. So it's equal to dp dt. m dv dt is dp dt minus v dm dt. Okay, and so then what is that? Well, dp dt, we calculated that. dp dt is equal to, yeah, that'll work out. So is equal to, let's write it as ve minus v times the magnitude of dm dt. Okay, that's what dp dt is. And then we subtract v times dm dt. dm dt is negative, so we can change that sign to a positive and put the magnitude of dm dt. Remember that when you put bars around something, you mean the magnitude, the positive value of that. Okay, so then you have a negative v times dm dt and a positive v times dm dt, so that cancels out that. And so you get this nice result that the thrust of the rocket, the effective thrust of the rocket, is the speed of the escape gas, the escape gas particles times the mass flow rate. How many kilograms per second of propellant you're pumping out the back. So what you really want to maximize, if you want to maximize the thrust that's acting on the rocket, which you really do, you want to maximize the rate at which you are dumping mass out the back of the rocket. You want to maximize how many cannonballs per second you can throw out the back, and you want to maximize how fast you can throw those cannonballs. And this really, for a chemical rocket, depends upon the particular chemistry. You're using liquid oxygen and or hydrogen and liquid oxygen, or RP1 and liquid oxygen, that kind of stuff. Okay, I did want to say one final thing, just to sort of really sort of drive home this whole point here. Maybe a clearer picture would be something like this. Okay, so my battery died there, telling me that I'm talking too long. But let me just sort of like summarize this really interesting point here. Okay, so we're going to start with the simplest situation is the rocket starts at rest out in the middle of empty space. And so what we do is, first of all, the rocket has a bit of a burn time, and so it got some chunk of mass of the rocket flowing to the left. Okay, so exhaust gas particles are moving to the left, and so there's a quantity of motion to the left. But the total quantity of motion is always zero, has to be zero, can't change. So that means that to compensate for this quantity of motion, there has to be a quantity of motion for the rocket, the rest of the rocket to the right. So now the rocket has some momentum to the right, it has some velocity to the right. Okay, so that's great. So this is, say, v equals 0 in this little diagram here. And then we throw out another chunk of rockets. We let the rocket burn for another 10 seconds or whatever. And so, but now those exhaust gas particles, because they are, the rocket is now in motion, those exhaust gas particles, their momentum to the left will be less in the original inertial reference frame. So we have a shorter vector over here. And so this is, we have added some momentum to the left to part of the system. So we have to add the same amount of momentum to the right, which is to the rest of the rocket. So the momentum of the rocket, the velocity and the momentum of the rocket goes up. All is good. And then the rocket's now moving faster. It throws out another chunk of exhaust gas particles to the left, but those exhaust gas particles are moving slower relative to the inertial reference frame, and so the momentum they contain, the quantity of motion, is even yet smaller, and so the amount of momentum added to the rocket to the right is even smaller. Okay, so for every same, say, 10-second time interval, the amount of momentum added to the rocket gets less and less and less. And so then finally, at this point over here, when the rocket has a velocity, let's just make one more, and then at this point over here, the velocity of the rocket is equal to the speed of the exhaust gas particles. And so then the exhaust gas particles, their velocity relative to the inertial reference frame is 0. And so they are at rest. So we've added no momentum to the system. So we added no momentum to the exhaust gas particles, and so there's no momentum added to the rocket. And so that is the rocket has a speed VE at this point, and it has maximum momentum. Because afterwards, when the rocket is now moving faster, and the rocket will always move faster and faster and faster, the exhaust gas particles, when they are released relative to the inertial reference frame, they're moving to the right. And so the next parcel of exhaust gas particles that's released from the rocket are actually moving to the right, and so you are adding some momentum to the right on this side, so you have to add a momentum to the left on this side. So the momentum of the rocket used to be this much, and then now it's being reduced smaller and smaller. Okay, and these actually get longer and longer until, let's say, this is burnout time. So at this time over here, we have V, let's call this, what do we call this? V final equals V max. So V final, which is the maximum velocity of the rocket, is certainly greater than the speed of the escape gas particles, but this momentum of the rocket that's left over, that momentum of the rocket, P final, is going to be less than P max. Okay, so that's kind of an interesting sort of picture. Sort of summarizes this whole discussion in a nice little diagram. So anyways, so much more could be said about this, but I think I've said enough about this. So this is a really nice application. The rocket is a great application of conservation of momentum. And it's important to sort of understand it in terms of, how do you think about how a rocket works in terms of, conservation of momentum in the form of, well, the total momentum of the rocket plus the exhaust gas particles never changes. That's one way to think about it. Another way to think about it is in terms of momentum transfer, a force acting over time. Thrust force acting over time imparts momentum to the rest of the rocket, what remains of the rocket. But it's also important to understand it just intuitively. The fact is, if you're floating out there in the middle of empty space and you have nothing to push against, well, you can't do anything. You can't go anywhere. You can't change your velocity. You can't, move your center of mass. You have to take a chunk of something that belongs to the rocket and throw it out the back. That's why rockets need a lot of mass. Okay, and they need something, some powerful sort of stored energy to get that mass moving really, really fast. Because you want to throw the mass of the rocket really fast out the back, and you want to throw it at a great rate out the back, kilograms per second, and it has to be moving fast out the back. That's what you do to maximize the thrust force. So anyway, so that's a little bit about the physics of rocket propulsion. Great example of momentum conservation.